Yeah, so we have a second panelist, Theo Laino from IBM Research, as Zurich. So Theo, please.
Absolutely. Thank you so much. And it's a pity that I'm not able to be there in person, but I hope you're having lots of fun. So I wanted to take these 10 minutes to give an insight of a work that has been led by a PhD student working in my team, Marvin Alberts. Of course, credits go absolutely to him. And is essentially something that we are exploring very recently, construction of foundation models for automated structure elucidation. Now, why is this important? Because, of course, I mean, we have seen even from the previous talk, you have to synthesize compounds that you are designing. But after the synthesis, there is another interesting step, which is the characterization. And the characterization, especially when you start going in high throughput experimental settings, can actually be very intense from a human perspective. And so synthesis planning with solutions like automated retrosynthesis, we as a team have been working a lot on RxN for chemistry, using already since more than 5 years a language model for synthesizing molecules, small organic molecules. And for the synthesis, you have automation and robotics, as we have seen before. For the structural elucidation, the situation is slightly different. There are plenty of analytical techniques. And of course, you can automatize the spectral acquisition, but quite often you are encountering the big hurdle of interpreting spectra, and maybe even different types of spectra. And so in terms of toolbox, analytical toolbox, definitely we do have NMR, definitely we do have mass spectrometry, different flavors, but there is also infrared. And I will start actually with the infrared in my description because it's one of those spectroscopy, which is a little bit the Cinderella in the analytical chemistry. I'll start from there and then I will cover the NMR. Today I will not, time reasons, I will not be talking about mass spectrometry. So there is plenty of work to combine AI with infrared spectroscopy, but most of this work are actually focusing on interpreting spectra to identify functional groups. And from NMR perspective, the situation is very similar. There is quite a few work around that try to identify within the NMR spectra the corresponding part of the molecule that is responsible for a specific multiplex, or maybe trying to the scaffold, and only very few work quite recently go all the way to try to build the molecular structure. So the NMR definitely is a field that from an AI perspective is more explored than the infrared. So can we do more? And more specifically, can we predict the chemical structure directly from spectra and all the type of spectra that we have said? And can we combine in a multimodal foundation model all the different spectra to provide a synergistic effect in having an higher accuracy in determining the structure of the molecules? So let's start from the infrared. We measure an infrared spectra and we want to derive from the infrared the structure of the molecule. Now, I'll just spend a few seconds here because this is a task that in general has always been denied to be possible, and essentially because the infrared spectra is very complex and not really subject to human interpretation. But in reality, when we started working on the infrared spectra, we wanted really to leverage the capability of algorithm in the space of AI to interpret the entirety of the spectra and come up with a recommended structure. I'll highlight here the workflow. The workflow is very similar for all the spectroscopy that I will show. And we always start from a random initialized model that is actually pre-trained using modeled and simulated data. So essentially what it means is that we are using for the infrared molecular dynamics for computing the dipole autocorrelation, doing a Fourier transform, and deriving the infrared spectra. For the NMR, instead, we are using a wide range of methodologies, starting from DFT to rule-based systems that are capable of simulating NMR spectra. This is important because the volume of data, experimental data that is available is actually quite limited. And you want to be sure that the model is pre-trained in capturing the correct physics. And then, of course, once you have the pre-trained model, you do the fine-tuning, and the fine-tuning model is essentially the one that I will be showing in the next. Also, we will be talking about the top-N prediction or scaffold top-N, which basically means among all the prediction of the model, we will be focusing on the first N predictions or the first N scaffolds. Now, how does it work from an AI perspective? First of all, we use a BERT model. We are encoding the spectra into a series of beam frequencies, and we are training the model in reconstructing essentially the spectra and the molecule using the masked language strategy. So essentially, we use a BERT model. And we started with slightly more than 600,000 model simulated spectra, reaching an accuracy of top 1, which basically means the molecule predicted with the highest accuracy was 45%, the overall top 1 accuracy. Of course, if you use this model in a zero-shot learning on experimental data, the accuracy goes very, very low. And this tells you that there is discrepancy between what you have been modeling and what has been measured experimentally. But the interesting thing was that pre-training was not meant to create a model that was accurate and perfect, but rather learning physics, the physics behind coupling vibration. And so when you just do a pre-training, use the pre-trained model on the model data and fine-tune on the experimental, then suddenly you recover essentially the same type of accuracy that we had on the original model data. So this is a very good result, and actually even the numbers are very interesting. These are some examples, for instance, of target molecules and the molecule that the system is predicting through only infrared spectroscopy. And we did a very similar thing for NMR. Same story, we codified the NMR into an annotated version, and we used a masked language for training the model in itself. And even in this case, top 1 accuracy, you can go all the way to 58, 57% for carbon-13 NMR. You can also do it for phosphorus. Phosphorus works in a slightly different way, just by looking at a radius around the phosphorus. But in this case, top 1 results are very good. The last slide, and I will stop it here within the 10 minutes, is essentially combining the two. So how does it work if you now start training a model of different modalities? You have the infrared, but also the carbon-13 NMR. Well, essentially, these are the type of results that you can expect. You can start from infrared only, reaching an accuracy of roughly 60%. Carbon NMR only, reaching an accuracy of 72%. And then combining the carbon NMR and the infrared, you can boost the accuracy of almost additional 5%. Now, the 5% may seem very small, but consider that this increase in performance is actually only by 2000 dataset point. So there is a really wide margin for exploring even further the capability of a model to predict the structure of a molecule, a catalyst, for instance, after the synthesis by combining different types of spectroscopies. Summary, I show you a little bit how you can play with AI, infrared spectra, NMR, hydrogen, carbon, proton, carbon, and phosphorus. Also, one of the interesting things that we will be working more in the future is the multimodalities. Thanks.